Hello and welcome. In this lecture, we are going to start studying composition in R2, composition of two linear transformations. Here are two linear transformations, the linear transformation S represented by a matrix A in the canonical basis, let us say, and linear transformation T which is represented by a matrix B. Okay. So, we know that the linear transformation S composed with T is represented by the matrix AB, we have seen that before. And what we are going to ask is this interesting question of how are the range and null spaces of the composition S composed T related to the range and null of S and T. So, supposing I know something about S, something about T, what can I say about S composed with T? What are the various possibilities? Okay, so, that is what we are going to study in more detail right now. Okay. So, let us see how to think of a composition in an abstract way in terms of the transformation. So, this is an important view of what happens when you compose two transformations. I will urge you to look at it and try and understand. It may not be very useful when you do computations. For computations, we will do other things, but this picture is good to have in your mind. So, basically you have to start thinking in terms of subspaces and dimension when you work in linear algebra. Okay, so, that is a bit of a shift. So, usually when you work with algebra, you just think of numbers, multiplying products. So, in linear algebra, you would always think in terms of dimension and subspaces. Okay, so, these kind of ideas are very important. So, we are going to look at that very closely here. Okay. So, if you want to look at the range of S composed T, how do you define that? It is basically, if you look at this very carefully, you take a vector in R2, for any vector in R2, you look at what happens when you hit it with T. So, you look at T of V, and then T of V is further hit with S. So, you get S of T of V. The set of all S of T of V for all V going through R2 is your range. Okay. So, how do I picture this? There are two steps going on here, right? V first gets transformed by T and then T of V gets transformed by S. So, let us draw it as a picture. So, R2, the entire space R2, when you are trying to find range, goes through T first. What do you get when R2 goes through T? You get range T. Okay. So, you get the subspace. The subspace R2, the entire plane R2 is going through your linear transformation T and you get the range of T. That is the output subspace when this goes through T. Now, what is happening when you hit it with S? The entire R2 is not going through S, right? Because S only sees the output of T. So, only range of T goes through S. Okay. So, this is where the slight subtlety comes in the composition. S will not see the entire R2, it will only see the range of T. So, range of T goes through S and you get the output. So, this guy can equivalently be written as S of V, but V now belongs to range of T, not R2. Is that okay? So, you notice how this subtle change has happened here. So, there is range of T and then there is range of S, which is S of V when V is all R2. Now, the range of S composed with T is S of V when V is restricted only to range of T. So, that is the picture that you should have in mind. So, this is range of S composed T, which is S of range T. Okay. So, I hope this picture is clear to you. This kind of visualization sometimes helps when you do it, and this kind of thinking in terms of subspaces is actually linear algebraic thinking in some sense. Okay. So, what is rank of S composed T? We need to think about this a little bit more. We will look at easy cases, difficult cases as we go along. Okay. So, this is range. Okay. So, what happens when you look at null? Okay, what is null of S composed with T? It is the set of all vectors V in R2 such that S of T of V equals 0, right? This is nothing but the definition, right? Null of any linear transformation is set of all vectors which give you 0 when transformed by them. So, S of T of V has to be 0. Now, let us try and draw a picture again in this fashion. Okay. So, I have S here and I have my origin here, right? I want the origin, right? After S, I want the origin. Okay, but what input will give me origin when I hit it with S? That is the null of S, right? The null space of S when hit with S will give you the origin. But that is not what I want here, right? I am not doing S of any vector, I am only doing S of T of V. Okay, so that is where this other confusion comes, right? So, I want set of all V in R2 such that this T of V belongs to the null of S. Okay. Notice the subtle change here, these two are equivalent, right? When will S of something be 0? When that something belongs to null S. Okay, so that is what I have written here. So, when will S of something be 0? When that something belongs to null S. So, set of all V such that the something T of V belongs to null S. Okay. So, what I want here is the null space of S compose T when transformed through T has to give you null space of S. Okay. So, this is a subspace, this is a subspace, this T has to be giving you null S. Okay. So, what should be null space of L compose T? That subspace which when transformed with T gives you null of S. Okay. So, that is the question. I do not know the answer to this question yet. I have to see it, but I do not know what the dimension will be. I do not know what it will be. But this is how you have to picture it. Okay. So, look at these two pictures and make sure you at least get a sense of what is happening here. When you are looking at the null of the composition, I want a subspace which will transform through T to the null of S. So, that when null of S goes through S, I get 0. Okay. So, that is the idea. And for the range, I am going to take the range of T, send it through S, and what I get is S of range of T. Okay. So, this is what is important, a high level picture of what a composition does. We are going to take individual examples, look at different cases of T and S and study this process and see what happens. Okay. So, let us get started with that. Okay. The easiest case turns out is when both S and T have rank 2. Okay. Both S and T are invertible transformations. They take R2 to R2. They do not do anything else, right? They may do many things to the vectors themselves, but the entire R2 goes to the entire R2. Okay. It does not change that. It does not reduce dimension. Okay. So, both S and T are full rank. Okay. So, you have linear transformation ST and the composition S cross T. Range S and range T are R square, null S and null T are origin. Nothing becomes origin. So, in terms of matrices AB, the product AB is there, matrix A is invertible, TB is invertible, S is invertible, T is invertible, and AB is the product. Okay. So, what happens when I compose here? It is very easy to see that the range of S composed with T and range of T composed with S will be both R2, right. So, R2 goes to T, okay, R2 goes through T. When T is rank 2, what happens to R2? The range T is also R2, right. So, the range is just R2 going through S and that is the same as range of S, and that will be just R2. Okay. So, when you have invertible full rank transformations, it is quite easy to see that the range is R2. Okay. Everything is full, right. I mean, when R2 goes through T, you get the entire R2, and that R2 further goes through S, you will get the entire R2. There is nothing that is lost, the dimension is never reduced anywhere, so you will get the entire R2. Once the range of a transformation becomes R2, you know that the null of those transformations is the origin, right. That is just from the rank nullity theorem, so it becomes origin. Okay. So, if you look at it in terms of the matrix, I know that the columns of A are linearly independent, columns of B are linearly independent. So, when you multiply AB, the columns of AB also become linearly independent because rank is 2, right. So, column space of AB is R2 and null space of AB is origin. Okay. This is just restating the facts about operators in terms of matrices. So, the easiest case for composing two transformations in terms of just how to find the range and null is when both S and T have full rank. When they have rank 2, the composition of S and T or T and S will also be R2 and the respective null spaces will also be origin. Okay. So, this is one of the easiest cases. Okay. So, now I am going to consider the case where the rank of T is 2. Okay. I do not know about the rank of S. Rank of S may be 2, in which case I know the easy answer, but the rank of S may be 1 or 0 or something, right. So, it can be anything else also. When rank of T is 2, what is going to happen? Let us see, right. R2, when it goes through T, I am going to get R2 again, right. That is my range T, right, because T is invertible, its dimension preserving, its rank is full. So, R2 goes to R2, no problem there. Now, when R2 goes through S now in the composition, I am going to get range of S, okay, and the range of S dimension is rank of S. So, when rank T becomes 2, it is as if T does nothing much and everything is up to S. Whatever S does becomes the range. So, range of S composed T is simply S of R2, which is range of S. So, rank of S composed T is equal to rank of S. Okay. So, S composed T is very easy when T is rank 2, right. It is quite straightforward to see that it is controlled fully by S. T just does the full transformation, it is controlled fully by S. So, once you have rank here, you can also find the nullity, but let us look at the null space more carefully. Okay. So, you have S here, and to get origin out of S, I need to come from null S, right. So, null S has to be there, so that when it hits with S, you get origin. Now, how do I get null S? Okay. but I know T is invertible, right? Once I know T is invertible, I have a T inverse. So, I can hit null S with T inverse and get T inverse of null S, and that will be my actual null space of S composed with T. So, because T is invertible, this I can find out which subspace which when hit with T will give me null S, right. So, that is nothing but null S being hit with T inverse, okay. So, that is a very easy thing to see. So, you see when T is full rank, T alone is full rank, the dimension, the range of S composed T becomes simply the range of S, and the null of T S composed T is the T inverse of null S. Okay, so this is again abstractly we are seeing. We will look at specific examples later on. Okay, so rank T equals 2 seems to be an easy case. Okay, so easy in the sense at least we have characterized it. Okay, so let's look at rank S equals 2. Okay, so we saw T being 2 was reasonable. T being 2, everything depended on S, right? So range completely depended on S. Null was nothing but null S. T inverse of null S was all you wanted. Okay. So now, if when rank S is 2, T may be general, right? T may do something. T may do whatever it does. So R2 through T gives you range T, and the dimension is rank T. And then range T goes through S, and you get S of range T. You can't say much more beyond this. Okay. So it depends on what range T is, and it goes through S. But dimension is preserved here. So whatever the range of T's rank may be, the same rank is preserved when you go to S of range T. So dimension is preserved, so the dimension becomes rank T. Okay. So you can find the rank of S cross T to be rank T. So previously when you had rank of S cross T, it was the same as rank S. When rank T was 2, now rank S is 2, and rank of S cross T becomes rank T. Okay. So T controls the size or dimension of the range of S cross T. So for the null space also something very simple will happen. Since S is invertible, rank S is 2, only the origin will give you the origin, nothing else will happen here, right. So origin inverted through S will give you only origin. So now how do I think of null space here? How do I get origin from T? That is just null T. Okay. So very easily we see that when S is invertible and S is full rank, everything is controlled by T. The rank of S cross T, S composed with T becomes rank T, nullity of S composed T becomes nullity of T. Okay. So we have considered 3 cases so far. S and T being full rank is very easy. One of them being full rank is also reasonably easy. The other one completely controls the rank and nullity of the composition. Okay. So the real interesting case is the next one, which is okay. So before we go to the real interesting case, let me conclude this part with restating these results in terms of matrices. Okay. So if in terms of the column space of AB is the set of all ABX for all x in R2. Okay. The null space of AB is set of all x such that ABX equal to 0, right. So this is what is going on with the column space and null space of AB. Okay. Now what is BX? BX is the matrix B multiplied by x1, x2, which is the same as x1 multiplying the first column plus x2 multiplying the second column. Okay, so this is a crucial fact about Bx. Bx is actually a linear combination of the columns of B. So any Bx belongs to the column space of B. Okay, this is a very standard property of matrix multiplication. If B is invertible, the set of all Bx such that x is in R2 becomes R2. Okay. So ABX, okay, set of all ABX such that x is in R2. Remember, Bx is all when x goes through all R2, Bx is also R2. So it is the same as AY such that y is in R2. So column space of AB equals column space of A when B is invertible. Okay, when B is invertible, this happens. Okay, so once you have the column space of A, the rank becomes the rank of A, right? Rank of AB becomes the rank of A. And then you can find the null of AB, which will also be equal to nullity of AB will also be equal to the nullity of A. Okay. On the other hand, if A is invertible, ABX is 0. We can look at the null space. Null space is easier when A is invertible. You can multiply by A inverse on both sides. So you get BX is 0. Okay. Whenever ABX is 0, you get BX is 0. Of course, whenever BX is 0, ABX is also 0. So this is if and only if. This goes both ways. So once it goes both ways, you know that the null space of AB equals null space of B. Okay. So notice this slight change here when you're looking at AB, if B is invertible, the range of AB, the column space of AB becomes the column space of A. That way you go to the rank of A for the range. When A is invertible, the null space of AB is much easier to quickly write down because that becomes the same as null space of B. From there you can go to nullity of AB. From there you can go to rank of AB. Okay. So, this understanding in terms of the matrix AB is also important. Understanding in terms of the operations or the transformations and what happens in the composition is also quite important. Like I said, this concludes the easier cases. The more interesting case, much more interesting case is when rank of S is 1 and rank of T is also 1. Let me conclude with a few examples. So, here are just simple products, product of two matrices here 1, 2 and 3. The exercise for you is to try and find the range of this and the null of this. Okay, so what would be the range in each case, what would be the null in each case, you can go through and find out the answer in each of these particular cases. Okay, thank you.